Hello students, I am back today with another important topics in class 11 that's called real gas. Actually it is gas laws, and gas laws contain two kinds of gas. One is ideal and real. A gas can behave sometimes as real gas and sometimes as ideal gas depend upon the circumstances. Now first of all, I discuss the case of ideal gas. Ideal gas are those gas which obey Boyle's and Charles' law. Boyle's and Charles' law. My intention of today's class is to discuss the case of real gas but not ideal gas, but a brief introduction of ideal gas I will provide to you. Suppose for Boyle's law, what we know? For a given mass of gas at constant temperature, pressure is inversely proportional to volume. P stands for the pressure. Pressure is inversely proportional to volume. That means when P is the pressure, V is the volume, relation is P varies 1 by V. So P is equal to K by V. So PV is equal to K. My intention is not to discuss the PV equal to K because all you know, but graphical representation of Boyle's law I want to discuss now. Suppose at a given temperature, if we make a graph P versus V, the graph will looks like rectangular hyperbola. Suppose it is T1, it is T2, it is T3. As we increase temperature, it moves away from origin. So in this case, I can say T3 greater than T2, which is greater than T1. This is one of the law P versus V. We know P is equal to K by V though. When P plotted against not V, 1 by V, it will be a straight line equation passes through origin. So P and 1 by V. So it will be a straight line equation passes through origin. Suppose it is at a temperature T1 and it is at a temperature T2. Now, suppose I have make a graph this way, P versus T. It is a case of Boyle's law. And what is the pressure law? Pressure law states for a given mass of gas at constant volume, pressure directly proportional to temperature. Why? Because if you increase temperature, more will be the collision between the molecules, more will be the pressure. So pressure law states for a given mass of gas, pressure directly proportional to temperature. Now let us proceed. It is pressure, it is temperature. In this along y-axis, it is the pressure, and along x-axis, it is the temperature. Now suppose it is given as V1 and it is given as V2. And the question asking which is more, V2 is more or V1 is more. It is a very easy question. You can easily answer the question. See, at a given temperature, it is at a temperature. So at this point, the pressure and the volume should be constant though. And again, on extending it, Again, at this point, pressure and volume should be constant, means here the pressure supposed to be P1, here the volume supposed to be, here the pressure supposed to be P2. Okay, let it be P2 and P1. So we can say P1 V1 is equal to P2 V2. Why? Because it obeys Boyle's law, temperature remaining constant is equal to K. Now from the graph we see that out of P1 and P2, P1 is larger. P1 is larger means V1 is smaller than so in this case V1 should be smaller than V2. V1 is this one and V2 is this one. V1 is smaller than V2. Hope you have followed it. If you don't follow it, you can write on my description box where I will provide my WhatsApp number. Now there is many things to discuss, but this class is mainly for real gas, so discuss the case of real gas. In deriving ideal gas, we have taken some approximation. Approximation taken at what? In deriving Boyle's law, in deriving ideal gas equation. What are the approximation? Number one, there is no force of attraction between the molecule. Between molecules. Number two, volume occupied by the molecule themselves. Is much less, is negligible compared to volume of container. These are the approximation taken, but this approximation is not always true, because in some cases ammonia or HCl or these gases on cooling converted to liquid. When gas converted to liquid means the force of attraction between the molecules is more than that of gaseous molecules. Hence, since there exists force of attraction between the molecules, and in all cases, volume occupied by the molecule themselves is not negligible compared to volume of the container. Okay. Now, if I taken into consideration the two facts that there exists force of attraction between the molecules, number two, volume occupied by the molecule themselves. Not negligible compared to volume of container. The law derived will be the case of real gas law. Real gas law taken into consideration of both the facts, that is force of attraction between the molecules and volume occupied by the molecule themselves. In deriving real gas, we have discussed a factor Z. Z is called compressibility factor. Z is equal to actual volume actual volume over expected volume. Expected means at a particular temperature and pressure. V is equal to RT by P. So PV equal to RT. This is the case of compressibility factor. Now, when I put Z versus P, I find this phenomena. For ideal gas, Z, that is PV, V observed by RT equal to 1. So the graph like this. For hydrogen and helium, Z is always greater than 1. Z greater than 1. Because there is hardly any force of attraction between the molecules. For some other gas, at low pressure, with increase in pressure, Z first decreases, become a minimum, then increases with increase in pressure. So, for ideal gas, Z is 1. For hydrogen, helium, Z always greater than 1 because there hardly exists any force of attraction between the molecules. For some other gases such as ammonia and carbon dioxide, etc., at low pressure with increase in pressure, Z first decreases forming a minimum, then increases with increase in pressure. These are the phenomena. Why the phenomena arises, all this can be explained when I discuss the case of real gas equation. A real gas equation was proposed by van der Waals and according to his name is known as real gas equation. So real gas equation is the van der Waals equation. Now let us discussing the van der Waals equation, but before that I want to explain some more part. When Z plotted against P at different temperature, what happens? For ideal gas it is 1. For real gas, suppose let it be at a temperature T1. See, in this case, suppose it is, let it be A1, it is A2, it is A3. Remember, higher the temperature, less will be deep. In this case, dP is maximum at the point A1 and correspond to temperature T3, and between A2 and A3 in A2, that is, let it be marked it A3 T3, A1 T1, A2 T2. Okay, see in this case A2 the dP is minimum, correspond to temperature T2, A1 dP is more than that at a temperature T1, and A3 dP is maximum, temperature is T3. So in this case I see minimum dP at T2, deep at T2. So T2 having highest temperature. And at A3 dP is maximum, T3 should be lowest temperature. So order, so T2 greater than T1 greater than T3. Now van der Waals equation, we have two correction terms. What are the two correction terms? One is a case of force of attraction between the molecules, correction terms, Van der Waals equation. Number 1, force of attraction between the molecule. Number 2, volume occupied by the molecules themselves. Occupied by the molecule themselves. Okay, let us see how we can explore all this part to you. Suppose this is a container. The molecules which are about to strike to the walls is attracted by molecules from behind. As a result, the force by which it will strike to the walls will be much less than it's supposed to do in the absence of attractive force. So listen carefully what I want to say. The molecules nearer to the walls which are about to strike to the walls will be attracted by the molecules from behind, as it will strike to the walls with much less force than it's supposed to do in the absence of attractive force. Is it clear? Now, number 1, the decrease in pressure due to attraction between molecules depend on number of molecules nearer to the walls. Number of molecules nearer to walls. More the number of molecules, more will be the force of attraction between the molecule, less will be the force by which the molecules strike to the walls, less will be the pressure. Number 2, decrease in pressure also depend on number of molecules striking to walls per unit volume. More the number of molecules in the system, more will be attractive force formed behind, less will be the force by which the gas molecules strike to the walls. In both the cases, decrease in pressure depend upon N by V. N by V in the first cases depend upon the number of molecule in the system. Second case, number of molecule which is about to strike to the walls from behind. So P dash proportional to N square by V square. P dash equals to A N square by V square. A is called force of attraction between the molecules. More the force of attraction, more readily it can be liquefied. A stands for the force of attraction between molecules. For N moles with a volume V. Now suppose it is a case of correction terms due to pressure. Correction terms due to volume will be what? Due to volume depend on number of molecules, number of gas molecules present in the system. So effective volume will be total volume minus the volume occupied by the molecule themselves. B is the volume occupied by the molecules, by a molecules. N is the total number of molecules. Hence the effective volume for movement will be total volume minus the excluded volume due to molecules, V minus B. Now, so real gas equation will be P observed pressure plus decrease in pressure due to attraction from behind, AN square by V square into V minus NB equals to nRT. It is a Van der Waals equation. Van der Waals equation for n mole of real gas. For n mole of real gas, for 1 mole of real gas, the Van der Waals equation will be P plus A by V square into V minus B is equal to RT. After that, A and B are taken as constant. The constant A arises due to attractive force between the molecules, B is due to volume occupied by the molecules themselves. Now I should discuss the unit of A and B. For n mole, I have done P plus AN square by V square. P has a unit of pressure, so AN square by V square should also have the unit of pressure. Let it be ATM, so AN square by V square. If I make it ATM, A unit will be ATM into V square by N square. So ATM into liter square over mole to the power minus 2 is the unit of A. What is the unit of B? NB should be same unit as V, that is liter. Unit of B will be liter mole minus. Now I can discuss why the deviation arises when Z plotted against P. Let us discuss this using Van der Waals equation. This is the Van der Waals equation I have taken for 1 mole of real gas. For H2 and HE, where A is negligible. A is the force of attraction between the molecules. Then P plus A by V square roughly become P. So P into V minus B equals to RT. So PV equal to RT plus PB on transferring PV this side. Now compressibility factor Z is equal to PV by RT. So PV by RT will be is equal to RT by RT plus PV by RT. That is 1 plus PV by RT. Is greater than 1. For hydrogen and helium, I find that Z value is always greater than 1. So these things can be explained using Van der Waals equation. Now I will discuss the case why at low pressure Z first decreases. Case 2, it is the case of case 1. Now I will discuss the case why Z decreases when P is very small. When P is small, V minus B roughly become V, and V minus B, if I make it to be V, is equal to RT. So PV plus A by V equal to RT. PV is equal to RT minus A by V. So PV by RT 1 minus A by RTV is less than 1. Hence, compressibility factor at low pressure first decreases, become a minimum, then increases with increasing pressure. It is a case 2. Third case, at low pressure and high temperature, what happened? Both A and B can be neglected. Then P plus A by V square into V minus B equal to RT. If I neglect both A and B, it becomes PV equal to RT. So real gas behave as ideal gas at low pressure where force of attraction decreases to minimum and high temperature when the volume occupied by the molecule will be maximum. This is up to for real gas. Next we will discuss some more topics.